33. What we have seen is in C++, there are different cast operators. There are four different cast operators: const cast, static cast, reinterpret cast, and dynamic cast. And every cast operator has a scope in which to operate. And C style casting is still available in C++ because of the backward compatibility. But certainly it is not advised that C style casting be used because it is not aware of the type, as well as it is not easy to see where it actually has occurred, right? So in this, we have discussed about the const cast, which is primarily to handle the uh, type casting with respect to constness or volatility, and primarily works on pointers and references. And we have seen several examples of that. Next, we will talk about the static cast and the subsequent ones. So this is a summary of the casting scenario. In C, we know we lose information. There's a lack of clarity of semantics. And in C++, we have seen that it could perform a fresh inference of type without changing of value, like const cast does that kind of thing. Or it can perform fresh inference of type with change of value, like implicit computation, which we are trying to minimize, and explicit user-defined computation. So we are going to talk now about the semantics of static cast and subsequent. So static cast operator is written starts with the keyword static underscore cast, has the same syntax, very similar syntax to const cast. It can perform all conversions that are allowed implicitly, not only with those with pointers to classes, but are also opposite to this. It can be, for example, it can convert a void star pointer to any pointer type. Implicitly, the reverse can be done. A pointer type can be cast to, will get cast to void star in the implicit manner. But you can actually use static cast to cast any kind of pointers, convert integers, floating point values, enum types, and so on. These are kind of in the C domain where static cast can make the semantics more clear and syntactic to capture. But it can perform conversion between pointers to related classes. Not only do upcast, but it can do downcast also, which is very, very risky. And we will see the difference with the dynamic cast very soon. But static cast should be used only for upcast, not for downcast, because when you downcast, you really do not know whether the object exists. And it cannot perform any runtime check, which the dynamic cast can do. So we'll talk about those. Additionally, static cast can also perform any user-defined casting. It can convert to R-value references. You still do not know what R-value references are. They are a feature of C++11, very important feature. Convert enums, any type to void, etc. So as usual, let's get to examples. So for built-in types, here you see that I have int I have double D, and I have a pointer to the double variable. So the double can be assigned to the integer. D can be assigned to E. It is an implicit, comes from C. It is an implicit casting where the compiler gives you a warning because you are going to lose information. You can do that without warning properly if you know that this is what you need to do. Hey, for example, you have computed some value which turns out to be a double having a fractional part, but you want always an integral result. Maybe you want a rounding on that value, so you could use rounding in that casting, and use static cast to do that. When you do that, the compiler gets to know that it is not by oversight that D is getting the value in D is being converted to a value in I from a double to an integer, right? It knows that you are aware that a casting function is getting called. Therefore, the compiler will not give any error. Of course, you could have done this by C style casting also, but it has all its problems, including that you cannot know where it has happened. If we look at the reverse, taking from integer to double, the implicit casting does not give warning because you are taking from a smaller data type to a larger data type. So you are not likely to lose information. Static cast would still certainly work well. C style cast you should not use, but will work well. Think in terms of assigning a pointer PD, pointer to double to integer. Now, why you would need to do that is a different question. There are programming scenarios where this is required. There are things like object serialization and deserialization, where you have an in-memory data structure and you want to write it out in the disk for future use. Then certainly when you write it out, you cannot write down the pointer values, because the next time when you are going to read from the disk and create that data structure, that same pointer addresses will not work because your memory has become different. So you would like to write some indicative reference numbers which possibly be integer, and for this you need to convert from pointer to integer or integer to pointer. This serialization is, just the simplest way to understand is, suppose you are editing a document in Word file and you do a save. So when you are editing the document, it is a data structure in the memory, right? So it has a whole lot of pointers and all that. When you do save, an equivalent form of that gets serialized, becomes a sequential file, and gets stored as your docx in the system. Now, naturally, there you cannot have the actual pointer values, because next, when you open that particular docx file, from that serialized form, you will have to recreate a new instance of the data structure, which you will be able to edit again. So deserialization will need a conversion from the indicative integer references to actual pointer values in memory. So this is just, it is, we are not talking about serialization, deserialization. These are important features of, again, software engineering, because you often need to write down a data, inline state of the program onto your disk and do the reverse. But just to give you a real scenario that you will need to convert pointers to integer. So if you do this by direct assignment, it is the implicit conversion is not allowed. So you get an error. You get a compiler error. If you use static cast here, you also get a compiler error. Why do you get a compiler error? Because the static cast does not allow conversion between unrelated types. You can convert between certain types of pointers. You can convert between certain built-in types. You can upcast, downcast, but you cannot take two unrelated type like pointer to a double and an int and do a casting. We'll see how to do this kind of casting in C++. If you do C style casting, it will still work, because it works in every case, but we will see the role of reinterpret cast in this matter. So this is a basic type of static cast operations that you can do for built-in types. Now let us look at the behavior of static casting in a class hierarchy, right? So I have a very rudimentary hierarchy. At the root, there's a class A, base class, and there's a class B, which is a derived child of class A. Public inheritance, everything is just a case of specialization. I have constructed two objects, one of the base class, one of the derived class. Now I have a base class pointer P here, points to A. I take the address of B and I put it here. So what I'm doing, I'm actually doing an upcast. I actually have a B class object, but I would be treating it with a A class pointer. So I would actually be treating only the base class instance part of B. So this is considered to be valid and it's implicitly accepted. This implicit is also okay, but we will not do that. Certainly you can do a static cast on this. So you're saying that my target is to take it to a class pointer, which is a type of P. You have declared here. And my source for casting is a B class pointer. So this is an allowed static cast. You can, of course, do C style, which you should be avoiding. The risky thing is you can do downcast. Now, if you do downcast, try to do downcast in an implicit manner. For example, you have, where is the declaration for pointer Q? That is missing. That should be put. I'm sorry. Here we should have B star Q. Okay. So Q is a pointed to the B class type that is more specialized, and you are trying to put. Please mute yourself, friends. Please mute yourself. And you are trying to put the address of a class object. So you are coming down in the hierarchy. So what it means, looking through P, you will feel that not only there's a base class instance, but there is also the derived class part available, but which actually is not, because the object actually is a class object, right? So by implicit conversion, this is not allowed. This is an error. But static cast will allow that. But the word of caution is do not use that. Do not use that. This will be risky. And there is a specific cast operator, dynamic cast, which will be able to do this. And it will do it with a lot of added semantics. But syntactically, this is performed. C-style casting can be done. It has no rhyme or reason of what it can cast. So it will allow everything. So this is the typical use of static cast in a class hierarchy. So you have seen a static class as one of the most common cast operator, operating on built-in types or operating on a cast hierarchy. So let me show you a little bit of kind of pitfall here. So let me see what we are trying to do. There's a window class which has a virtual method on size, and there's a special window class derived from that, which has actually overridden this virtual method on size, right? So special window has to do something something special and over the window class. So it has overridden that. And so what you are trying to do is you are trying to take this object, the special window object, and what you want is you want to call the on resize of the window class, the base class, right? So what you take is start this is a special window object, and you are casting that to window. So you're saying it is a window object, right? And then do on size. The sliced object, the problem is that this will compile, but the problem is when you do this casting, certainly you are creating a new object, right? What you wanted is you wanted to call on resize of the window class on the base part of the special window instance you have. But what this will do, this will create a temporary object, window object, which is the sliced version of your special window object. And it will call the method on that object, right? So whatever will happen on that temporary base class object, not in the base class part of your special window object. So if you have to do this, then you can directly call this method by qualifying its full name. So on the override of special windows on resize, you could call window : on resize, which will certainly call the on resize method of the window class on the special window instance, right? So be careful about you may think that, okay, I want to do a resize, so let me take it to the base and then call that. That kind of thing will not work. You'll always have to remember that type conversion is not a passive activity. It is a computation. So the moment you do a casting, certain objects are involved, and most often these are temporary objects till you actually use them. So when you convert a double to an int by static cast, or for that matter any cast, a temporary object is created from that double with integer type, and then that object is assigned to I. So through that assignment, that temporary object is used and then forgotten, so you do not see any bad effect. But here you are directly calling the on resize on that temporary object, so you will have a major difficulty. It will not work in the right way. Okay, so that was about the hierarchy. Let's see what happens if we try to do static cast on unrelated classes. So I have two classes, A and B. They are not related by a hierarchy. I have A and B objects. I have an integer which is 5. And then I try to cast from B to A. So whatever way I do, whether I do a direct try and direct implicit one, or I try a static cast, or I do a C-style casting, all of these are errors. You cannot cast a unrelated type, one unrelated type object into another class, another object of another class, if you do not have a way to do that casting. Okay, now let us look at the right hand side. On the right hand side, what I have done is constructors for class A, and the application part looks the same. Now if I do A assigned B, what it means is I have a B object and I need an A object. So this is a scenario of construction. So if there is a constructor that can take an A or B object and construct an A object, that constructor will get called. So this will be valid, and this constructor, which takes const B reference, will take the reference to the B object and construct the A object, and that A object will be assigned by copy assignment operator, default or defined by you, into the A object. So it uses this constructor. The same thing will happen with static cast. The same thing will happen with C-style casting, right? So casting between unrelated classes are possible if you have a constructor from the source class to the destination class, right? From the right-hand side object class to the left-hand side object class. Similarly, you could do this from the built-in type. You can do int to A also. What will happen? This constructor will get used. A int I defaulted 0. This constructor will get used. So if you assign, then A colon colon A int gets used. You can do by static cast, by C-style cast. All of this will work, right? So the cast operator actually inherently may call the constructor of a class if it needs to use the object of one class and convert the type to object of another class. So it actually does not convert the type. What it does, it takes it as an input and as a parameter class for the constructor, parameter object for the constructor. Such a constructor has to be available, and then constructs a new instance for the target class object and uses that object. So that is the basic meaning of the static cast operator in unrelated classes. Okay, now so I have done this left hand. So here this was the earlier. Here, if you see, I was trying to. This is the earlier slide we were doing, slide 9. We are trying to convert from B to A and int to A, and we have shown how to do that in a proper way. Now, here we are trying to again convert B to A, which is same, and I'm trying to convert I to A to int. Earlier, I was trying to do int to I. I'm trying to do A to int. That if I have a class object, it has a int component. I've put an int component. So what probably I mean is I want to extract that component by this casting. So if I take a class object and try to assign static cast, C style cast, all of them are errors because unrelated things cannot be cast. Now there is a very interesting feature which you can use to do this. In A class, if I want that an A class object be castable to an int type, then I can give what is known as a int cast operator. This is again an operator, right? So what does this operator mean? This operator is written exactly in the same way as other operator, but the difference is the operator symbol here is the name of a type. Type means it could be a built-in type or it could be a class name. So you write operator int. What it means is that you want to apply this operator on a class object to get an int type object, right? So it is kind of a reverse construction, you can say. So you can take an A type object, make it int. Similarly, you can do that for B class. You can put an operator A and say that this operator can take a B class object and convert it to an A class object. That is, create an A class object, right? So this is what this is saying. So this is known as cast operator. Two things are notable in this, in the signature of a cast operator. One is there is no operator symbol. It is a type. The symbol, in place of symbol, you have a type that you are casting to. And the second is there is no return type given in a operator, cast operator. There's no return type. If you had done a casting for, say, operator plus, you will have a return type, say, A for class A, adding to class A object. You did fraction. So you had a return type called fraction, right? Which is the return type of operator plus. Here you do not have a return type. Why you do not have a return type? Because you do not need a return type. Because what is this operator int saying semantically? It is saying that it belongs to class A. So it will take a class A object and create an int object. So obviously by the name of this type, you know what is the return type. It will always return an object of this type. Operator A will always return an object of A type. And now you can use them. So now if you take a B class object, like the scenario before, make an assignment. This assignment is valid, and what it does, it invokes this cast operator A of the B class. So B colon operator A. Similarly for the static cast, similarly for C style casting. We will certainly try to avoid both of these. You can do that for int, operator int of A also. You can take A and assign it to I. What the compiler finds that A belongs to class A, which has a conversion operator to int. So it invokes that operator. Similar things happen to static cast and C style cast. So the one way casting can be done through constructor. The other way casting can be done through operator, cast operator. And both of them could be invoked through the static cast operator in terms of the source and. So if you have a source and target classes, like in general scenario of a static cast, what you need is either the source class will need an operator for the target class, like you have here, or the target class will have a constructor which takes the source class object. If either of that exists, then you'll be able to do this casting, right? So this was about the static cast operator. So let me pause for a while and see if you have questions. These are apparently straightforward, but you have to be very careful in terms of what you cast into what, because casting, once you have cast, it takes on a different semantics of that type. And the key thing to remember is every cast operation is actually a cast operator call of some form or other. Either that operator is defaultly given or that operator is explicitly written by you. And as a result of that casting operator, in many a times, initially a temporary object is created, which is then given to your target object. So you have to be careful that you don't happen to write something like the window case and end up using that temporary object, right? Is there any question, friends? No. So let me then continue and let me, we are back to the presentation. We are on slide 11, which has a reinterpret cast. Reinterpret cast can convert any pointer type to any other pointer type, even of unrelated classes, which static class cannot do. It can only do between the hierarchy, upcast, which we should do, downcast, which we should not do. The operation results in a binary copy of the value from one pointer to the other. All that it simply does, it just makes a binary copy of that bit. It does not do a kind of a computation to do that. All pointer conversions are allowed. It can also cast pointers to or from integer. So what it does, it takes the pointer pattern and starts considering that it is an integer. It does not do a computation. That is why it is reinterpret. What do you interpret? In terms of your type, you are interpreting the bit pattern that you have. That bit pattern per itself does not mean anything. The meaning comes from the type you know that the bit pattern has. So in reinterpret, what you say that I have a bit pattern, I know it belongs to, it is an instance of this type, but I want to give a new interpretation to it. What this I knew to be a pointer type, but what if I interpret it as an integer? I interpret it as an integer and use it as an integer. So naturally, the guarantee required is a pointer cast, that a pointer cast to an integer type is large enough to fully fit into that. So in many systems, the size of the pointer and the size of int are same. If they are not, particularly if int is smaller, then you will have this will get rise to problems which you will not be able to figure out easily. These conversions can be done by reinterpret cast, but not by static. So I have two classes, A and B, unrelated, and integer double pointer. We have seen that it is an implicit error to cast a pointer of double to int. We cannot do that. But I can do a reinterpret cast. The static cast was giving a failure here. In the reinterpret cast, what it does, it takes the bit pattern of PD and just thinks it is an integer, puts it to I. Right? Similar thing can be done by C style cast. You can check out the do the C out and see on the C out, the first data will be printed as if as a pointer. The second data will be printed as if as an integer, and they will be eventually same. Now for two unrelated classes, I have A and B, two types of pointers. If I try to assign one to the other, it is an implicit error, but I can do a reinterpret cast. I can take a B pointer and reinterpret it to be an A pointer. Right? Now why I do that? On context, certain very restrictive situations only. Normally, never. So static cast does not allow it because this is very risky, because this does not make a normal sense of programming. Naturally, C style cast allows almost everything. So reinterpret cast, the main use of reinterpret cast is this particular assignment, where you take a pointer and cast it to integer, or you do the reverse. You take an integer and cast it to pointer. And of the applications that I know are all variants of serialization, deserialization, packetization, depacketization. Like you have a data structure you are trying to do a remote execution. So you need to send your instance of the object to that remote system. Naturally, it has to go through the network layers. It has to get packetized within that. And here you have the data structure with pointers and all that. So they will have to be, again, in some way serialized, packetized, transmitted to the remote system, depacketized, deserialized. A new instance replicating your instance has to be created in the remote machine. So only in that process you will need this. So if you just try to see that in an application, it is very, very unlikely that you will have the use of this cast operator. And if you are having to use that, question yourself 10 times as to why are you using it, or you are using it in an inappropriate manner. Right? So this is a static and reinterpret cast that we have studied. So let's now get into the next, the fourth and the probably the most interesting cast operator, which is called the dynamic cast operator. So we are talking about the dynamic cast operator. So we are here in the dynamic cast. Now, dynamic cast operator cannot be used on any kind of data. They can be used only with pointers or with references to classes, or with void star, of course. Its purpose is to ensure that the result of the type conversion points to a valid complete object of the destination pointer type. So you're taking one pointer and creating another pointer. This pointer points to some object, and your resultant pointer points to probably a different object. But it has to be a complete object on the destination. This naturally includes pointer upcast, converting pointer to derived class into pointer to base class, which you normally would do with a static cast. But it can do downcast, and it can do downcast on a polymorphic hierarchy. And that's the most important thing. That is where you need it, because you need to, often, since a hierarchy is polymorphic, often what you're holding to that object is just a pointer of the base class type. You do not know what has actually been instantiated. Inside, it could be any derived class object. And if you want to go to that particular class to explore or to use more of the members, data members, and methods of that class, which you cannot do with a base class pointer, you will need to downcast. So downcast can also be used for a reference type. We'll come to that. First, let us look at example. So we have a class A. We have a class B, which is a specialization of A. And we have a class C, which is unrelated. We have ABC objects. We have PA, PB, PC pointers. We also have a void pointer. So this is a. Now, if I do assign the address of B to PB, which is a normal assignment, the same type. Now I do a dynamic cast from PB to A star. Now what is the B? B is a specialized class, derived class. A is a base class. So if I'm doing that, I'm actually doing an upcast, which is valid. I could have done a static cast. I should actually do a static cast because it's statically convertible. It's no matter what B class is. Second, what I do is I take the same object, B object, the pointer of that, but take it to a class pointer. Right? This is allowed. This assignment is allowed by implicit upcast. Right? Now I want to get back. So what I do is I take this PA, A class pointer, and try to cast it to a B class pointer. This is a case of downcast. I have information of it being in the A class, but I'm going to treat it as a B class. This will be perfectly okay. Think about the next. The second and third, you should watch very carefully. What I did is initially here, I took a B class object and put that pointer to A. Here I have taken an A class object and put the pointer to A. And I have again tried this. Now this downcast is invalid, because if you say I will treat this pointer as a pointer to a B class object, you actually have an A class object. So this is going to be invalid. So what the dynamic cast does is something very, very simple. When you are doing this downcast from A to B, where after casting, the pointer will point to really an actual B class object, it will return the same pointer value as PA. Just that its type is now pointing to the B class object. Or in some cases, it might change the value also. That's a different domain of multiple inheritance and all those. But in this case, where the casting is invalid, it will return you a null pointer because it is not valid. Now, this is the dynamic behavior. So if you look at syntactically, both these right-hand sides of casting look syntactically the same. They are called on the same object, PA, which is a pointer to a type. But their behavior is different based on the runtime value of PA. That is, what is the object that PA is actually pointing to. That is the reason you call it a dynamic cast. Whereas this first case is being done by a dynamic cast, but could have been done by a static cast also, because every B class pointer can be treated to as a class pointer because you are just using a part of the information. So this is the core idea of dynamic casting. Now C is another class. So I take a C object, forcibly cast that address to A class. Because this is unrelated, I cannot do any kind of static casting or anything. I forcibly do C style. And then I use that to get the C type object. Since these are unrelated in the hierarchy, this is not valid. So it's an unrelated cast, which is as well. Okay. So what you'll get, the behavior is dynamic cast will again return you a null pointer. Another example, you are taking a class object, putting it to A, and you are casting it. I'm sorry, there was another. Then there's, okay. Now think about this, that if PA is 0, it's a null pointer. And you have done a dynamic cast to C star, this particular case is valid. Because no matter what the type is, if the pointer value is null, it means the same thing for every pointer type. It means that there is no object. So this will be valid because PA is null. Now, again, you take a class object and you try to cast it to void star. So what you are saying that this was a pointer pointing to a class object, and now I am treating it as a pointer where I do not know what it points to. So you are basically having more information and you're going to use only a part of it. The part of the information is just saying that it is a pointer. So this is valid. So cast to void is always valid. Casting from null is always valid. Cast to void is always valid. But if you try to do the reverse, if you take a void pointer and try to do a dynamic cast to A type, this is an invalid expression for a dynamic cast because the source pointer of the dynamic class has to be a class on a polymorphic hierarchy. Otherwise, dynamic cast cannot work because it is doing downcasting. So it is doing a downcast dispatch. It needs a polymorphic hierarchy. Right? So just try this out. Obviously, you will not get the same pointer values in the output as I show here, but you will get equivalent values and you will get the same final result. The interesting thing is dynamic cast can also be used with references. So I have class A, I have class B, which is specialization of A, I have class C, and I have 3 objects A, B, C, and forget about this try part right now. So I create a reference for B. And then I say that I'm taking this reference and I am converting it to a reference of A type. So what I'm doing, I'm going up. Upcast, this is valid. Typically, you should do by static cast. Now I take this B, but I create a reference of type A. So RA3 will be considered as a class object, not as a B class object, even though the reference is actually pointing to a B class object. Now you take that reference and try to cast it to a B class reference through dynamic cast. This is a downcast which is valid. Right? So this is upcast is always valid, but should be done by static cast. This downcast in this case is valid. So you can do downcast on pointer as well as reference. Now the question is, what happens if the downcast is not valid? That is, instead of taking a B class object, you have taken a class object and you have a class reference to that. And you are trying to cast it to B class reference, which is not possible because this is an A class object. Now the difficulty of, when you did this for the pointer, you had the option of returning a null pointer. But when you are doing it with a reference, you have to return a reference. There's nothing called a null reference in C++. You have to return an object. So that is not possible. So what it does, it throws an exception. We'll talk about exception in the next, possibly tomorrow itself. So what it does, it says that normal flow cannot work, and it throws an exception which is known as a bad cast exception. It's a bad cast. If casting you tried, it cannot be done. And when you write this try catch block, what the try catch does is anything you put inside the try clause, if that throws an exception, then the execution of the code, is kind of halted at that point, and you transfer the control to the catch clause. So if this fails, this will fail, you will get a bad cast exception thrown, which will be caught by this clause, and this particular message will be printed. Now this is important. We'll talk about exception at lot. This is important because this is actually a true computation error. You cannot proceed with this computation with this kind of a downcast, where you are actually having an object which is not of the type to which you are trying to downcast to, right? So exception becomes handy there. So we will talk about that separately here. It came up as a part of this. Similarly, if you try to do something with the C class by forcibly creating a class reference to a C class object, and then try to cast it back, you will have again unrelated casting error because of unrelated classes. You'll again have a bad cast error, right? So this is how the dynamic cast operator can be used. So this is very, very important. Now the question is, why does it need a polymorphic hierarchy? It needs a polymorphic hierarchy because in C++, once you have created an object, there is no way to know what is the class for which the object has been created. An object is just a bit pattern. Right? So if I have a complex class, I've created an object, then looking at that object, I will not be able to say whether it is a complex type object, or it is just a pair of tuple, or it is something else. It could be, kind of 6 integers also packed one after the other. When I have a polymorphic hierarchy, I have the advantage that every class has a virtual function table. And as we have discussed, that virtual function table is unique for that class. So if I have an object coming from a polymorphic hierarchy, then that object's instance will have the pointer to that virtual function table of that class. And that pointer is the identity of the object to say which class it came from. Right? So that information is what the dynamic cast uses to see whether actually a downcast is possible. Otherwise, it gives null or throws bad cast. So there is an operator available in C++ known as typeid operator, by which you can actually know this information in your program if you need to know that. So where you have a dynamic type of polymorphic object. Naturally, type ID will not work for non-polymorphic object for the reason I said. And you can do a static type identification. So type ID operator can be applied to this. It is returns a const type info. Type info is a data structure. through which you get that information on the type. And you can check. Please mute. You can check for equality. You can get the name. So these kind of things you can do on this type ID operator. Obviously, for this you need a runtime management, because those virtual function table pointers have to be put at the runtime to the object. You are not specifying that by the value. So it needs an RTTI, runtime type information system, to run, which the C++ supports. I mean, we won't get too much into that for now. And if the polymorphic object is bad, then the type ID will throw a bad type ID exception. So let's see an example. So I have a class A, which is which has a pure virtual destructor. A virtual destructor. So it's a root of a polymorphic hierarchy. Then I have a specialization in B. I have an A object created, and I do a type ID on A, and it returns me the type info. You can look into this type info header. This is available in C++, where the type info is available. You take the name part of it. So it gives you the name. It says class A. Right? Very nice. It tells you what is class. If you do it on type ID ampersand A, then you're treating with a pointer of A. So it gives you a class A star. You take a pointer P, put this address there, do a type ID on P, then you get similar class A star. If you dereference that pointer, you will get a class A object. So you say name is class A. Take a B object, do type ID and address, you will get class B star. You take a type pointer and put this address in that, and then you take type ID on this pointer, you will get class A, because it is actually a pointer to class A. But when you do dereferencing, when you do star P, then you are looking at that object, and that object actually is a B class object. So it says class B. Very interesting case, where if you get to know the type of the pointer, you are getting to know one thing, but when you dereference, you are actually having an object of a different type. That's what this polymorphic hierarchy is telling you. Certainly, you can do similar things with reference. You have a reference on A, you have a reference on B, and as you print, it will give you class A, class B, this kind of. Right? And naturally, if you invoke type ID on something which is not on polymorphic hierarchy, it's not a valid one, then it will throw a bad type ID exception. So this is our polymorphic hierarchy, very familiar. Engineer, manager, director, the salary application. This is a this is slide 11. This is a non-polymorphic hierarchy. This is a hierarchy, but this is non-polymorphic because there is no virtual function. Right? So this is so when you try this, look at this line. The similar to the earlier one, Q is assigned ampersand Y. Q is a pointer to the base class here. Y is an instance of the derived class. So when you print the type of Q, you get X star, this fourth line. 1, 2, 3, 4, fourth line X star, which is right. Now, here what you get is you are doing star Q, class Y object, but you do not have a polymorphic hierarchy. Since you do not have a polymorphic hierarchy because there is no polymorphic method, so the virtual function pointer virtual function table pointer is not there in class X or class Y. So the system at runtime has no way of knowing what is the type of star Q. So it does not print class X, class Y, it prints class X. Earlier, 2 slides back when we did this, it was printing class B, the actual object type. Here it is printing just the dereferenced version of the pointer type of base because it has no way to determine that it actually is a Y class object. So that's the difference between using type ID or dynamic cast operation on non-polymorphic hierarchy. They really does not make much sense. So this is a case of bad type ID. You have class A, you have specialized to class B, and PA, new of A, you are doing PA class A star, you are doing star PA, you are getting class A, you have deleted PA, fine. Now you are trying to do type ID PA. Type ID PA is the type of this pointer, which is valid. So you get class A star. But when you do type ID star PA, then you have actually deleted it. So at the runtime, there is no object now pointed by PA. It still has that address. You have not set it to 0, but it has a bad object. So it catches an access violation because as soon as you delete PA, the corresponding runtime data gets deleted. So there is no RTTI data on this. So what you get is a bad type ID exception thrown from this. So which is caught and access violation given. The last case where after delete, we actually set it to 0. If you do a type ID on PA, you still get class A star because that's, but when you do star PA, type ID on star PA, you're basically doing null pointer dereferencing. So you're trying to get type ID of a null pointer, which is not permitted. So, which obviously does not make sense. There is no runtime object. So how do you find the type? So you again get a bad type ID thrown. Right? So this is the behavior of the so this is something in depth in terms of dynamic hierarchy, because downcast is something that you are going to require at several places where you need to build a logic based on the actual runtime instance of the object that your base class pointer is pointing to. Or you may want to give some message, good message in terms of your errors and all. You need to find the type ID and get the name from that. So on polymorphic hierarchy, which is going to be the mainstay of our design, which is the mainstay of the object-oriented design, we have seen the way to move up the hierarchy through static cast, and we have seen an intelligent, smart way of moving down the hierarchy through pointers or through references using the dynamic cast operator, and what are the associated errors and exceptions involved, which can be handled subsequently. So I will stop here. If there are any questions, I'll try to answer. Any questions, friends? No questions? You have understood the casting very well. That's good. That's really good. So to summarize, we agree that we will not use any kind of C-style casting. We'll try to avoid using implicit casting even if it's allowed, and certainly never use an implicit casting which creates a warning, right? And we will restrict ourselves to using const cast to handle constness with a lot of caution, static cast between built-in types where it is allowed, and between types of related classes primarily, and for upcasting, dynamic cast for downcasting on a polymorphic hierarchy. And reinterpret cast, we will know it exists, but we will really question when we are about to use that. Okay. So this was about quality of data type that we have talked of here. So if there is no question, let me stop here today. Tomorrow morning, I will talk about errors and exceptions, which is a very, very critical area for any software engineering task. That how do you handle the errors and exceptions in your development, and how to make safe, good quality code using the whole concepts of exception safety. Okay.
Sir,
Yes.
sir, in dynamic casting, that in polymorphic hierarchy, why we are not using a scope resolution operator to define which object belongs to which?
It's 1 second. Could you tell me which slide you are referring to?
Dynamic casting,
Yeah, dynamic casting has about 7,
polymorphic,
8.
polymorphic.
Dynamic casting. This one.
Uh,
Right?
yes, sir, this one.
So what is your question?
Sir, you told that we don't know about which object belongs to which class. So why don't we use scope resolution operator?
No. I mean, we do not know that in general. You have a class A. You have created an instance. You have a bit pattern. How do you know that it is created from class A? It could have been from
Okay.
any other class. I have a class A which has one data member which is int. Right? If the int size is 4 bytes, then I create an instance of class A. I'll have a 4-byte bit pattern. If I create an instance of int, I'll have a 4-byte bit pattern. If I have any other class which has a single int data member and I create an instance, I'll have a 4-byte bit pattern. Looking at the bit pattern at the runtime, how do I know which class was used to create this bit pattern? Right? That information is not there. If you know Java, do not get mixed up there. Java has a runtime system all through. So Java's runtime tracks every object creation, and the runtime system keeps that information. C++, for all efficiency, does not afford those overheads. So only if the hierarchy is polymorphic, you need the virtual function table to dispatch your virtual functions. And that virtual function table pointer is unique for the class and same for all objects of that class. So you make use of that information to in the runtime system to know what is the type of that bit pattern. Otherwise, you have no way. Are you getting me?
Okay, sir. Means instead of using scope resolution operator, we are referring to the virtual function.
I mean, we are not directly, it is an internal of the information, but I'm just conceptually saying that where do we know it from? Why do we know it if it is a polymorphic hierarchy? Why don't we know if it is an isolated class, if it is a built-in type, or if it is a hierarchy which is not polymorphic? In none of these, you have additional information which is dependent only on the class. In everywhere else, the information is dependent on the data members, which I can have two classes having identical set of data members, and there is no way to distinguish from the bit pattern that the object came from which of these classes. But when it is a polymorphic hierarchy, to support polymorphism, I had to use the virtual function table, which is unique for the class. And that pointer has to go into every object. So the object has a virtual function pointer field from where that information is conceptually available. Then how it is implemented, how this is extracted is a differently long story. Okay.
Okay, sir.
Okay, then we are completely out of time. So I'll stop here. We'll meet at 8 o'clock tomorrow again and start the discussion on exceptions. Have a nice day. Bye.